My name's Jeff Lestz. I'm a postdoc at UC Irvine, and this is some work that I did with collaborators at Princeton on the topic of the nonlinear evolution of kinetic instabilities due to dynamical friction and large effective scattering. So the motivation for this work is that wave-particle interactions are sensitive to collisional dynamics. This is both a fundamental plasma physics problem, and it also has a fusion application, which is developing reduced models for fast ion transport. The goal of this work was to understand the influence of drag on the nonlinear evolution of an instability in the presence of large effective scattering, which I'll define later in the presentation, and is also a common tokamak regime. So the role of drag and chirping has been explored extensively, but less so for steady-state solutions, which is the focus of this work. The main results are that we now have new analytic solutions for the 1D electrostatic bump-on-tail problem near marginal stability in the limit of large effective scattering with drag. Namely, drag increases the saturation amplitude and also shifts the oscillation frequency. A quasi-linear equation for the perturbed distribution naturally emerges from the nonlinear theory, and also drag fundamentally modifies the resonance function, leading to shifting and splitting. So the outline of my talk is here. First, I'm going to introduce the Burke-Breisman cubic equation, and then I'll move on to the amplitude evolution with drag, which comes from a time-local cubic equation that we derive. Next, I'll go to discuss the perturbed distribution function, which involves the spontaneous emergence of a quasi-linear system. And lastly, I'll talk about implications for the resonance condition and future applications. So the starting point for this work is a 1D electrostatic kinetic equation where we include both diffusive scattering, which is characterized by this parameter nu, and also convective drag, characterized by alpha. Now, it's important to point out that nu and alpha are effective scattering and drag rates, which are enhanced within the small resonance region relative to the 90-degree pitching while scattering and inverse slowing down times. In the kinetic equation, there's a wave electric field that's monochromatic, and it has a complex mode amplitude characterized by E hat, which we'll want to solve for. And so I said this is a bump-on-tail problem, so we'll be analyzing near a region in velocity space where the fast ion distribution has an approximately constant positive slope, which is proportional to the drive for the modes. So the first goal is that we want to decouple the evolution of the wave field from the distribution function. And to do this, we will perturbatively expand this equation in the small parameter that's the bounce frequency divided by the scattering frequency. And this is guaranteed to be small so long as you're close to marginal stability. So if one does that, then they will arrive at the Burke-Breisman cubic equation written here, which gives the leading nonlinear effect on the mode amplitude evolution. So this first term is obviously just linear growth, and then this is the leading order nonlinearity, which is third order in the mode amplitude, hence cubic equation. And it really contains a lot of rich nonlinear physics. And this is partly because it's an integral over the time history. So these time delays lead to time correlations. And then the kernel of the integral contains information about the collisions. And together those can lead to rich nonlinear physics depending on the size and type of collisions you have. And so this is a very important equation because it's really been a paradigm to interpret nonlinear experimental phenomena, such as in TFTR and JET shown in these figures. So the cubic equation admits both steady state and dynamical or non-steady solutions. And the type of solution depends on the type of and the amount of collisions that you have in your system, as shown in this figure. So if your system has more scattering, then it's going to tend to have more quasi-steady solutions. Intuitively, this is because diffusion tends to smooth out phase space structures. Conversely, if your system has more drag in it, then you can't have steady solutions, and then you might have more dynamical solutions, such as frequency chirping. And the intuition here is that convection tends to preserve coherent correlations. It just drags them through phase space, and those coherent structures can support nonlinear phenomena. The effect of drag on chirping has been explored quite a lot recently, but what hasn't been previously investigated is how the steady state solutions in this region are modified by drag, and that's the main focus of this work. So onto the amplitude evolution. As a reminder, this is the Burke-Breisman cubic equation that I wrote a few slides ago, and this is valid when phase correlations in the kinetic equation are unimportant. That is, the bounce motion is much slower than the scattering frequency. Now, if on top of that assumption, you also make the assumption that the effective collision rate is large relative to the growth rate, then time correlations also become unimportant. And this leads to a much simpler equation because basically if this nu hat parameter is much greater than 1, because nu is greater than gamma, then the kernel of the integral becomes very peaked around small values of z and x. And so that makes these time delays basically irrelevant. And so then to leading order, you can ignore them and pull out the mode amplitudes. And that leads you to this ordinary differential equation for the amplitude evolution, which we call the time local cubic equation because it doesn't involve an integral over the time history. And then here, all of the collisional physics are contained in this integral constant b. And the other thing to point out is that this extra assumption of scattering rate much greater than the growth rate, this is really a typical tokamak regime. Past calculations have shown that this parameter is of order 10 or more because it includes small angle collisions and turbulence. So this is a very relevant assumption to make. Also, this time local cubic equation can be solved exactly. And to do that, you want to split up the complex mode amplitude into its magnitude and also its phase. And so doing this, you can find closed expressions for the amplitude and the phase at all times, and that gives you the complete solution. And in particular, this can tell you things like how does the saturation level depend on the amount of drag and scattering in your system. I'll show that in the next slide. But interestingly, if you have any amount of drag in your system at all, then in the nonlinear phase, the phase of the complex mode amplitude will start to evolve. And at long times, it'll just lead to constant oscillations, which shows up as a finite frequency shift in the apparent oscillation frequency. It just gets added on top of the linear frequency of the mode. Now, as it turns out, both of these quantities, the saturation amplitude and the frequency shift, are increasing functions of the amount of drag in your system. In other words, drag is destabilizing. It leads to a larger saturation amplitude. And our predictions are shown for these block curves for saturation amplitude and frequency shift as a function of the ratio of drag to scattering. As you see, both of these functions, they start out pretty slow, so that the effect is not large until one approaches the boundary between the steady and non-steady solutions, which is when drag becomes comparable to scattering. We also compared our predictions to fully nonlinear 1D kinetic simulations, which are these data points shown for different parameters, and we find quite good agreement. Just to give you an idea of what these solutions actually look like, I've first shown an example here of a numerical solution to the Burke-Breisman cubic equation for the complex mode amplitude. So here the blue curve is the real part of the amplitude, orange is the imaginary part, and then gold is their magnitude. So you see there's this initial linear growth phase, and then a small overshoot, and then eventual saturation. Meanwhile, once the mode has approached saturation, the phase starts to evolve in time. It's no longer completely real. And eventually, you just get this pattern of regular oscillations. That's where this frequency shift comes from. Now, on top of this, we can overlay our analytic solution to the time local cubic equation, and we find that there's quite good agreement. So for the magnitude, you see it's basically right on, though it misses this overshoot. That's a next order effect. And then it also captures these oscillations, albeit with a phase lag, and that's also a next order effect. And we've shown that both the phase lag and the overshoot error go to 0 in the limit of nu hat goes to infinity. So that's the story of the amplitude evolution. Now what about the perturbed distribution function? So really interestingly, if you make the same assumptions that the bounce motion and the growth rate are much slower than the scattering rate, then the time evolution equation that you get for the spatially averaged perturbed distribution function is identical to a quasi-linear system, which is written here. So this is a diffusion equation with collisions, and then this underlined portion gives you your quasi-linear diffusion coefficient, and this script r, which we call the resonance function, and I'll show on the next slide, gives the velocity dependence of the diffusion coefficient. So this is pretty remarkable because typically quasi-linear theory requires you to make an additional assumption that you have some type of overlapping resonances to make the theory valid, to destroy the coherence. But what we have shown is that so long as you are near marginal stability and you have sufficiently large collisions, then the kinetic theory is actually equivalent to the quasi-linear theory, even if you have a single isolated resonance and even in the presence of coherence-preserving drag. So this is quite remarkable. Now that resonance function, which gives the velocity dependence of the diffusion coefficient, we've now calculated self-consistently from first principles, including both scattering and drag, and that expression is given here. So this is something that you would need in order to do realistic quasi-linear modeling, for instance, of fast ion transport. Just to give you some context for what this object is, if you didn't have any collisions at all, then the resonance function would be a delta function right at the phase velocity of the wave. Now, if you had scattering collisions only, then that would broaden the resonance about that phase velocity proportional to the amount of scattering in your system, but it would still be symmetric. Now what we've shown is that because drag breaks asymmetry in velocity space, because drag drags things down, this leads to shifting the peak of the resonance function, which is shown here. So as you add more drag into the system, you lose the symmetry, and instead the point of strongest wave-particle interaction shifts downstream. So instead of the strongest wave-particle interaction occurring at omega minus kV equals 0, it now occurs at omega minus kV equals something having to do with the amount of drag in your system. And this has consequences for the perturbed fast ion distribution that you get, which is given by this expression and then shown in this figure for a different amount of drag to scattering. Now, if you have no drag in your system, then you have this blue curve, and you see that it's symmetric about omega minus kV equals 0. If you add progressively more amount of drag going from orange to yellow to purple to green, you see that upstream of the resonance to the right, you get this well structure that forms. And so this is very different than if you don't have any scattering, if you don't have any drag in your system. And it's interesting because there's this big change in the perturbed distribution function, even though the resonance function doesn't seem to change all that much. I mean, it does have this qualitative difference, but these are quantitatively similar. And so this demonstrates that really the fast ion transport really does care about the details of the resonance function. So we've compared these predictions against the fully nonlinear simulations. That's shown with these black curves for each case. And we find excellent agreement so long as you are close to marginal stability, which is where the theory is valid. Now I'll move on to implications for the resonance condition. So in the earlier parts of the talk, I brought up two distinct frequency shifts. The first one was that drag will modulate the real part of the mode amplitude. That's illustrated in the spectrogram, where initially you start out with this linear oscillation frequency, and then as the mode evolves, the largest frequency in the spectrogram actually changes, and it tracks our analytic prediction. So this difference is that frequency shift. Now, the other frequency shift is that the peak of the resonance function shifts downstream as you add drag to the system. So these are actually not the same thing. These are two different frequency shifts that appear, but they're related through the resonance condition, which is written here with time dependence. And so the interpretation is that the resonance function is the same at all times. So you always have this right-hand side. But what changes is that the frequency of the mode changes as shown in the spectrogram. And so the most resonant velocity must also change in order to satisfy this equation. So really these two frequency shifts do have some impact on the resonant wave particle dynamics. Everything up to this point, we've assumed that there's less drag in the system than scattering, and that was intentional because we wanted to study the steady solutions. But we realized that actually all of our calculations are also applicable for the early phase of what will become non-steady solutions. So we asked the question, what happens if drag is much greater than scattering? And what's interesting is that if you look at the resonance function, as you add more drag to exceed the amount of scattering, in addition to continuing to shift downstream, the resonance function also splits into having many peaks of comparable magnitude. And so there's many regions in phase space that have strong wave-particle interaction when you have drag much greater than scattering. And then this has an influence on the perturbed distribution function that you get, which inherits these striations. And so this pattern, these aren't propagating, it's not oscillating or anything. You just have these striations that are sitting there, and then they get stretched as the instability grows. And I'll also point out that this isn't the saturated perturbed distribution function, because the theory wouldn't be valid there when there's this much drag. But this is what you get in the early growth phase. And so the question in our mind is, how are these features which show up early on and are very unique, how are they connected to the system's eventual nonlinear fate? Does this set up, for instance, preferential conditions for frequency chirping? That's something we'd like to explore in the future. Now I'd like to talk a little bit about where one might expect the effective drag to be important. So from heuristic scaling arguments for the effective scattering and drag rates, you can get the dependence of this key ratio alpha over nu on background plasma parameters. Though this leaves out an important factor, which is that turbulence further enhances the scattering rate, which would decrease the ratio of alpha over nu as well. And in fact, in conventional tokamaks, it seems that the turbulence is so large that typically drag will be much weaker than scattering due to large turbulence. But the takeaway is that the influence of drag is relevant when alpha sort of becomes comparable to nu, when drag is comparable to scattering. And so there's two main ways this can be achieved. One, if you're in a situation where turbulence is relatively weak. So for instance, in spherical tokamaks, they're known to have less turbulence, or also in negative triangularity experiments on D3D, there was less turbulent transport. These are situations where it's already been observed that there's a greater tendency for frequency chirping, which indicates the importance of drag. And secondly, because of this strong dependence, if the resonant particle energy is much larger than the plasma temperature, drag could be important. Now, of course, this is always the case for energetic particles, but if you have some situation where it's unusually larger, then that could enhance alpha over nu. So for instance, for alphenic modes, the resonant velocity is proportional to the alpha in speed, proportional to the magnetic field strength. So if you're going to construct a future high field tokamak, one might expect that the effective drag would be more relevant than in modern devices. And then going in the complete opposite direction, in basic lab plasma experiments, the temperature can be so low that this strong dependence can lead to drag to also be relevant. And that's where we think it might be a good place to test the predictions of our theory. So just to summarize, the problem we studied was the nonlinear evolution of instabilities in the presence of drag and large effective scattering relative to the growth rate when one is near marginal stability. The main outcome of this work is that we have a new evolution equation, the time-local cubic equation, which can be solved completely analytically, and it gives new insights. Namely, drag increases the saturation amplitude, and it also introduces a frequency shift in the apparent oscillation frequency. The perturbed distribution function satisfies a quasi-linear system, demonstrating a profound connection that nonlinear theory actually reduces to quasi-linear theory when scattering is much greater than the growth rate. And lastly, the resonance function can be shifted and even split due to the effective drag. So for future work, we'd like to determine ways to test the predictions of this work in basic plasma experiments where one can have fine control over the plasma parameters. And also we'd like to explore the consequences of the resonance splitting for non-steady solutions and connect that to the different types of nonlinear behavior that's observed in plasma experiments. And with that, I'll thank you for your attention.